Hello and welcome to this lecture. In the previous lecture, we got introduced to this analysis method called hypothesis testing, and it seemed interesting. We saw some simple problems where we had different hypotheses, and we looked at how to decide between them based on samples, information that samples give you. So we looked at things like significance level, which quantified one type of error, the other metric called power, which was like the 1 minus some other probability of error, another type of error, the two types of errors, and all of that we looked at. Now I'm going to sort of do a rough classification, or just put out a few ideas that typically show up again and again in hypothesis testing. Okay, some types of tests which show up routinely. Whatever problem you may take, whatever initial starting point you may have, invariably you will end up doing one of these tests. Okay. So this section is just to give you the definitions from high level. You can just go through it very fast. It's not meant to go deeper than that. Later sections we'll take each of these things and look at them a little bit more closely. Okay, so this is just to give you an idea of all the type of tests that are there. Okay. The first thing is to classify the hypothesis itself. Okay, so the hypothesis so far we said basically it gives you it makes some assumption or states something which you want to assume about the distribution of x, right? You have n IID samples and you want to make some statement about the distribution of x. That's your hypothesis. Some hypotheses are said to be simple. So what is simple? A simple hypothesis will uniquely specify one distribution for you. Like for instance, the distribution is normal with mean 0 and variance 1. Supposing you say a hypothesis is like that, it's a specific distribution. Like for instance, it may say the distribution is Bernoulli half. Okay, it defines one precise distribution. Some hypotheses like that are said to be simple, and they're simple to deal with also in some sense. It's exactly one, right? So that's a simple hypothesis. Here's an example. You may, if you're doing coin toss, you may say probability of heads is 0.5 or 0.9 or any one value. Okay, so not multiple values, just one of these values. Okay, same thing with normal. If you're looking at normal mu comma 3 samples, you may fix one value of mu. You may say mu is equal to 1 or mu equal to minus 1, something like that. Okay, so that's a simple hypothesis. In some problems, your null hypothesis will be simple. Your alternative hypothesis will also be simple. Both of them will be simple. Now, these kind of problems are the best understood. In fact, one can argue that the best possible approach for these problems is known. But in most situations, these kind of simple null versus simple alternative rarely occurs. Okay, so nevertheless, it's a good example of a hypothesis test where we know the answer, right? So it's always good to have a problem where you know the answer completely and well. So that's a nice thing. Okay, so what we will look at next are maybe not so simple, but nevertheless it's good to know the simple situation. Okay, so this is the one type of hypothesis, which is simple hypothesis, and as the word implies, if your hypothesis is simple, usually testing for it is not too complicated. Okay, so that's one way of thinking about it. The other type of hypothesis is composite hypothesis. So usually the alternative or any other, even the null for that matter, may be composite in nature. Okay, so you don't uniquely and completely specify the distribution. You may say a normal distribution, but you may have a range of means. You may say mean is greater than 10. Okay, or you may have a Bernoulli distribution and you may say p is not equal to 0.5. Those kind of things are composite distributions, where the distribution is not uniquely specified. Maybe the class of it is specified, but the distribution itself is not uniquely specified. Okay, so here are some examples. Okay, so you may have situations where the null hypothesis may be simple, but the alternative hypothesis is not simple. Okay, so you may want to test whether a coin is fair or unfair. Right? This is very typical, isn't it? Why would I know 0.5 or 0.6 precisely? Sounds a little bit fishy. I mean, it's not so clear that it's 0.6 exactly, right? So maybe you want to say probability of heads is 0.5 is the null hypothesis, but my alternative hypothesis is probability is not 0.5. It seems a little difficult to test against these kind of things. Some people don't like these kind of tests, but it's more practical, I would say, right? So maybe you have a measure of how unfair it is, etc. But even you may say, it should be greater than 0.6 or less than 0.4, not exactly 0.6 or not exactly 0.4, right? So something like that might be a normal situation. Same thing with even Gaussian samples. Supposing you have normal distributed samples, if some effect is not there, like for instance, if you're measuring something, if let's say you have a communication equipment, you turn it on, you'll hear noise, okay? And if somebody is talking at the other end, you'll hear a signal. So your normal hypothesis may be what you're hearing is Gaussian distributed with zero mean. There's no signal from the other side. The alternative may be that there is some signal from the other side, some strength is coming from the other side. So this kind of situation happens very routinely, and even here you have composite hypothesis. So you may have a simple or a composite null versus a simple or a composite alternative in some sense, right? So there are lots of studies on this. There are multiple approaches possible. Okay, so different types of approaches will give you different types of answers. It's difficult to show that there is only this approach that works. You can sort of quantify, but you can sort of theoretically define some good approaches, but many of them may not exist, and there's all sorts of issues once you have composite hypothesis involved. But this is most common. Okay, so in the next few slides, I'm going to describe some typical scenarios where you have some very typical hypothesis, and just leave it at that. We won't look at tests or anything. Just put out some very standard problems that show up again and again and again, and we'll see how to test for them and how to say something about those hypotheses in practice. Okay, so let's get started with that. So this is all standard tests. I'll refer to them as standard tests. There are various other terminologies. You'll see the terminologies will keep coming. There'll be a lot of jargon, but at the heart of it is always samples, null hypothesis, alternative hypothesis, and that's it. Okay, so always focus on that, and you'll get a clear idea of how to classify it. Okay, so here's a situation where you have IID samples. There is some, maybe the distribution has an expected value. It also has a variance. Okay, so this is a very common situation, and there is something called testing for the mean. Okay, so if your hypothesis is about the mean, like for instance, your null hypothesis might be that the mean equals some c. Okay, and you may want to have an alternative hypothesis, which is of different varieties. You may have mean being greater than c as one alternative hypothesis. Another type of alternative hypothesis might be the mean is less than c. Another type of alternative hypothesis may be mu is not equal to c. Okay, and in each of these cases, there can be two different possibilities. One is the possibility where variance is known. The other is the possibility where variance is not known. Okay, so this kind of a problem, once again, we are defining it in a purely theoretical setting, but this is a very standard problem, and you'll see any practical problem you take, you break it down, eventually you'll have something like this. Okay, you'll have a situation where there are random samples, and maybe their variance is known or not known. We don't know about it. Both cases are possible, but you want to say something about the mean. You want to hypothesize something about the mean as part of your analysis. You may say the mean is equal to c, or you may say the mean is greater than c. The alternative may be mean is greater than c. So this situation shows up quite often, and like I said, in the next few slides, we'll simply define situations like this in theory, theoretical situations, and later on we'll see some problems which break down into this eventually, right? So that's how we'll approach. Okay. So you may also test for variance. Okay, so these kind of problems are called one sample problems. You have one sampling, right, x1 to xn with one distribution. You have one sampling, and you have to do some tests. Okay, you may want to test for the mean, in which case the hypothesis is about the mean. The alternative itself, the null hypothesis, is about the mean taking a particular value. The alternative may be multiple possibilities. Mean is greater than that value, less than that value, not equal to that value. So quickly you can see that the coin toss example was something like this, isn't it? If it's not composite alternative hypothesis, alternative can also be that mu is equal to c, some other c, right? So it means c plus 10 or something like that. It's also possible, but this is testing for the mean is very standard, and you should have some standard methods for doing it. We'll see later on some standard methods for doing it. Okay, you may also test for variance. Okay, what is test for variance? I don't care about the mean so much in these samples. I want to have a null hypothesis, which is that the variance is equal to some number. The alternative may be the variance is greater than some number. Okay, So notice I'm always looking at composite alternatives. The reason is simple alternative, we'll deal with it later. Okay, so I'll come back to it later. Simple null, simple alternative, like I said, it's a well-known problem. People know how to approach it. There's very easy ways to write down the standard approach. We'll come back to it later. What I'm going to talk mostly about is cases where you have simple null maybe, but the composite is a little bit more, the alternative is composite. Okay, so that's how we are going to look at it. Okay, so these are the standard one sample tests. You may want to test for the mean or test for the variance. The null may be that the variance is greater than the value you're trying to test for, or even in the mean case, you may have different types of alternatives. Okay, so hopefully this is clear. Once again, the setting is theoretical right now, so you'll see later on. We'll see how some practical questions may translate into this. Okay, so you may also have two samples tests. Like, so for instance, you may have one set of samples, n1 samples, which you think are according to one distribution with one mean and one variance. Another set of n2 samples, which are maybe according to some other distribution, maybe, right? And the mean is something else and the variance is something else. Like, for instance, a very typical scenario, you're counting tigers, let's say, right? So you go into one forest, you're doing some counting of tigers. You're going into another forest, and then you're doing some counting of tigers. Maybe you are after a number which is number of tigers per square kilometer or something like that, right? So you have one set of samples here, one set of samples here, and you want to compare which forest has more tigers, things like that, right? Very natural setting. So you see how two samples can also arise quite naturally, right? The one sample case is also typical, but you may have two samples also, data arising from two samples also like this, and you may want to compare these two samples. How do you compare two samples? You may want to compare the mean. You may want to say, my null hypothesis is that the two means are the same. Okay, so this situation shows up in so many other areas also, but let's just understand it from a theory point of view. Your null hypothesis may be mu1 equals mu2, and the alternative is mu1 not equal to mu2. Okay, so you can even quantify it. Your alternative may be that absolute value of mu1 minus mu2 is greater than something. You can have alternatives like that which are more precise in some sense, but generally mu1 not equal to mu2 is the alternative. Okay, so this is comparing two samples, two means. You can also compare variances. Okay, so there are cases where variances are interesting to compare. You may have once again a null hypothesis which says the two variances are equal, and the alternative may be some form of not equal exactly, or maybe the ratio of the variances is greater than something. Sigma 1 by sigma 2 is greater than 1.5, for instance. You may have alternative hypothesis like this. Okay, so once again, one sample, two samples. In the one sample, you may test for the mean, you may test for the variance. In two samples, you may test for the means being equal and the variances being equal. Okay, so these are very standard simple cases. You have samples and standard types of hypothesis, and we should have methods for all of these things. What is going to be our method? How are we going to test for this, right? So how are we going to decide the acceptance region? How are we going to decide the rejection region? How are we going to compute significance level? How are we going to compute power of the test? How are we going to decide how many samples we need? All of these things, right? So that's the analysis that we will do for these cases. That's coming up soon. Okay, the last type of hypothesis test is very, very popular, is goodness of fit testing. Okay, so you have samples. I want to know if the samples follow a certain distribution. Okay, so we already saw this before when we did parameter testing and all that. You're given data. I want to fit the data to a Poisson distribution. I want to fit the data to a geometric distribution. I want to fit the data to a gamma distribution. How did we assess goodness of test? We found the best possible parameters, assuming it's gamma, and then we looked at the histogram, and on top of that we plotted a curve, and then visually we looked at it and said, okay, this looks good, so this is a good fit. Okay, but that's not very precise, is it? I mean, you don't get a sense of quantification of how good the fitness is. Okay, so very, very standard hypothesis test. The goodness of fit is also proposed as a hypothesis test. Okay, to the samples follow a certain distribution. So for instance, if you have integer samples, positive, non-negative integer samples, you may ask the question, is the distribution Poisson? So what is the null hypothesis here? The null hypothesis is, supposing you say these are all IIDX, we say X is Poisson lambda. okay, for some lambda. It could be any lambda. I don't care what the lambda is, but the null hypothesis is that it's Poisson lambda. What will be the alternative hypothesis? X is not Poisson. Okay, so this looks a little bit bizarre. You know, the alternative not Poisson. It's like anything else, right? So yeah, very big alternative hypothesis set, but that's the hypothesis. Okay, so this kind of goodness of fit testing is also very common. You may have continuous positive samples, and a very natural question is the distribution gamma? Once again, I don't care about the alpha and beta, the parameters of the gamma. Whatever I get, I'm happy with, but is it gamma? Okay, it's a very important question. And if you have continuous distribution minus infinity to infinity, okay, maybe I should put like this here, okay, then in that case, is the distribution normal? Normality testing is very important and popular. You have samples. The first thing you want to know is it normal or not? Okay, so how do you build tests for that? So generally, goodness of fit testing is this kind of testing is called goodness of fit testing. Okay, another case which frequently occurs is your distribution is multinomial, as in each xi is from one of m possibilities. You can call it various things. Some people call it categorical variables, this, that. There are lots of names for these kind of things. One of multiple possibilities. And you want to hypothesize that there is some hidden factor theta, and every probability. So this is probability that xi equals 1. This is probability that xi equals m. Okay, you want to hypothesize that the first probability that xi equal to 1 depends on some theta. Okay, in some way it could be, I don't know, one simple way of doing it is 2 by 3 into 1 minus theta, things like that, right? So maybe this is just 1 by 3 into theta, like that. Okay, this is an example. Okay, so some function of some parameter theta, which you for some reason you might know that there is some hidden parameter theta which controls all the probabilities, and with some function of those probabilities I know what the functions are. Okay, so this is a very common situation as well. You have a certain multinomial distribution that can occur, and once again you're doing just a goodness of fit test. You want to see if distribution like this is a good fit. We saw ML problems like this, right? So ML estimation problems like this. So you have a distribution like this, find the best theta, right? And after you find the best theta, how good a fit is it? Okay, so that's a very natural question in hypothesis, and maybe you need a few methods for answering it, or generally also you may want to answer the question of goodness of fit without even finding the parameter, maybe, right? So who knows, it might be there. Okay, so these are the standard types of hypothesis tests. Let me summarize it for you. You may have one sample and you may want to test for the mean, you may want to test for the variance. You may have two samples, you may want to compare the means of the two samples, you may want to compare the variances of the two samples. The last is goodness of fit. Okay, you have one sample and you're sort of trying to look at the histogram, and you're trying to guess the distribution, and maybe you can fit even a distribution to it. You get some parameters. How do you know how good a fit it is? Okay, so these are the standard types of hypothesis tests, and for each of these in the ensuing lecture or so, we will develop a precise testing method. Okay, at least we will describe a precise testing method and its properties. What are the properties? Significance, level, power, some other property which is called the p-value. Okay, so before we start thinking of properties of hypothesis test, so far we had type 1 error, type 2 error, quantifying that. There's one more type of quantification for hypothesis test which ends up being very important. Okay, and to motivate that, in the next lecture we will start looking at some practical questions which you may want to answer using hypothesis test, and we will look for something there. We'll look for error probability and what is beyond that. It turns out there's one more important characterization of hypothesis test, and that I will introduce in the which is the p-value, which we will introduce that in the next lecture or so. Okay, thank you very much.